Hi grade 12s. Topic 1 was introducing compound angles and looking at deriving some of them and playing around with them. And now what we're going to go and do is some more exam type questions. How could we actually use these compound angle identities in questions? So here's example 1. Example 1 says determine the value of sine 15 without the use of a calculator. Now remember, the moment we hear the word without the use of the calculator, I'm assuming I need to use special angles. And so my question to myself is there a way to rewrite 15 using special angles? Now normally I've had to say to myself, is there a way to rewrite 15 using an axis? Because the only tool that I've had is to use reduction. And reduction only works off an axis. So I've always had to say, is there a special angle that I can add or subtract to an axis angle, so 180 or 90 or 270, 360 to rewrite 15. Now for the first time we have the ability to do this, but we don't have to use an axis because we have compound angle identities. So can you rewrite 15 degrees using two special angles? Now I can think of two different ways. We could either say 60 minus 45, or we could say 45 minus 30. Now it doesn't actually matter which one you use, you'll land up with the same answer. You sometimes land up with something which looks different because it's all surds, and if you can mess surds around quite a bit, and so they look different, but it's exactly the same value. So if you ever get an answer which isn't identical to the memo, just put it in your calculator and get it to a decimal, and put the memo in and get it to a decimal and just check they might be the same. Right, now there's an identity which is sine of angle 1 minus sine of angle 2, and the identity says this: we sine the first angle, so sine of 60, times cos the second angle, which is 45, minus cos the first angle times sine the second. Now, so that's quite new for us. We've had to use reduction before, but all of a sudden we have compound angle identities, and so we can use that to expand this sine of a minus b into just using special angles. Now sine of 60, you can use your calculator if you really want, because I won't know whether you checked, but sine of 60 is root 3 over 2, cos of 45 I think is root 2 over 2, cos of 60 is a half, and sine of 45 is also root 2 over 2. So you always land up with a whole bunch of surds. So this becomes root 3 times root 2, which is root 6 over 4. This is minus root 2 over 4, which is actually just root 6 minus root 2 over 4. Now it's hard to tell whether surds will simplify, so often what I do is I just pick up my calculator and I put that in as a surd, and I've just checked, does my calculator write it a different way to me, to check whether it can be simplified. We prefer to have the denominator being a rational number, so that's why we do a whole bunch of rationalizing the denominator. But this denominator is rational, it's 4. And so I would put that in my calculator, and my calculator tells me that it cannot be simplified any further. Now, if you had done this, what would my answer have looked like? My answer would have looked like sine the first angle, so sine 45, times cos the second, minus cos the first, sine the second. Now, this is going to land up in exactly the same answer as that, because sine of 45 is root 2 over 2, and cos of 30 is that. And cos of 45 is root 2 over 2, and sine of 30 is that. So you'll actually land up with the same answer. So don't let it worry you about which one you choose. So that's quite a common exam question, something like that. So don't forget that up until now we've always had to say to ourselves, how can we use an axis? Now we can say to ourselves, is there an option to use an axis, or is there an option to use special angles? Okay, let's have a look at another one. Prove that cos of x plus 60 plus sine of x plus 30 equals cos of x. So this is fairly nice because I have an identity for that. It says cos the first angle times cos the second angle minus sine the first angle sine the second angle. Don't forget to make yourself a little cardboard cutout of these identities because you use them all the time. There's actually going to be two extra identities which we're going to do fairly shortly, and then you can add that to the list as well. Now this is sine the first angle cos the second plus cos the first sine the second. Now this said prove, so you can't make that equal to cos x. We're trying to show that this equals cos x. Right, now let's see if there's any like terms. This is cos of x cos 60. There's nothing like that. Nope, there's no like terms. And so what I would do is just use special angles. Cos of 60 is a half, so I get a half cos x. And what do you know? Just further down the line, sine of 30 is a half. And so this is also going to be a half cos x. And so I'm assuming that those two will add together to give me cos x. So what happens in the middle here? This, let me choose a different color. This sine of 60 is root 3 over 2, so this is minus root 3 over 2 sine x. And this other one, sine of 30 is also root 3 over 2, so it's plus root 3 over 2 sine x. So what happens is your two middle terms end up cancelling each other out, and your two outer terms are like, and a half cos x plus a half cos x is just cos x. So again, a good exam question just to check, can you do special angles, can you apply identities? It's really quite nice. Okay, let's look at the next one. Prove that sine of 5a plus sine of 3a is 2 sine 4a cos a. Okay, now where did that come from? We don't have any 5a's in our answer. So how can you rewrite 5a? Well, you could rewrite 5a as 2a plus 3a. You could rewrite 5a as 4a plus a. You could rewrite it as 6a minus a. There's lots of options. Now, how do I know which option is best? Well, let's look at what I'm trying to work towards. I'm trying to work towards using 4a and a, which means immediately I know my second option is better. I also then would look at my 3a and I would say, can I rewrite that? And again, I want to use 4a and a simply because that's what my answer has in it. So what I'm going to do, remember this isn't equal, you're trying to prove it's equal. So sine of 5a plus sine of 3a. I'm going to rewrite 5a. Of all the options, I'm going to choose 4a plus a because if I look at the answer, that's where I'm going. And 3a, I'm going to rewrite it as 4a minus a again because your proof is working towards 4a and a. So now I'm going to use compound angle identities. This is a sine compound angle, so it's sine the first term, first angle times cos the second angle plus cos the first angle times sine the second angle plus, now I'm probably going to run out of space here because these things are so long, so plus sine the first angle cos the second minus cos the first sine the second. And I'm hoping some of these are going to cancel out. So if I look at, now I wrote b there, which was very silly because there's no b's in the question. So let me go change that to a. And now I've got some like terms because I've got plus cos 4a sine a and then minus. So those cancel each other out. These two are identical. So I have two of them, which is 2 sine 4a times cos a. So this looks really easy, and it is easy, but setting up and figuring out what they're trying to get you to do is the hard part. So just a hint here, always look at where you're going. I'm trying to prove it's got something to do with 4a and a, which immediately tells me that my 5a and my 3a needs to be rewritten using those two angles. Okay, let's try another one. This is a really important one. Example 4 is pretty much where we're going to pick up in our next lesson. So this question says, prove that cos 2 theta is 2 cos squared theta minus 1. So in tomorrow's lesson, this is going to be called a double angle identity. And it's going to be really important. And so I thought it might be nice just to go about proving it. So again, this is exactly the same as example 3 in that I have 2 theta here, but I want to only have it in terms of 1 theta. So how can I go about rewriting 2 theta using theta? Well, I would have to rewrite it as theta plus theta. Now the identity says that you cos the first angle times cos the second angle minus sine the first angle times sine the second angle. So this actually becomes cos squared theta minus sine squared theta. Now that's not what they wanted. They wanted 2 cos squared theta minus 1. So this sine squared theta has to go. And hopefully you remember there's another identity which says that sine squared plus cos squared is equal to 1. So sine squared of any angle plus cos squared of any angle equals 1. So if I want sine squared, I can just subtract the cos squared. So sine squared is the same as 1 minus cos squared. So if I go and replace that sine squared with 1 minus cos squared, it now becomes minus 1 plus cos squared, which is what gives me the 2 cos squared theta minus 1. Now again, tomorrow we're going to revisit this idea because that is a double angle identity which is going to be highly useful to us. So I thought we'd just prove it for fun. Okay, let's look at another one. Example 5 says prove that cos 80 plus cos 40, which are not special angles, is equal to cos 20. So my first thought is I have reduction at my disposal. Can I rewrite 80 using an axis and a special angle? And I can't. Can I rewrite 40 using an axis and a special angle? And I can't. And especially important, I can't rewrite them using 20 in an axis because 20's got nothing to do with 80. And so let's have a look. Can you rewrite 80 using 20? Why 20? Because that's where I'm going. So how could I rewrite it? I could write it as 100 minus 20. The problem is that would then involve using cos and sine of 100. And 100 I know nothing about. So instead of using 100, could I rewrite it as 60 plus 20? Now why that's favorable to me is because I know 60 is a special angle, which means I can work with sine and cos of 60. So that gives me a hint for cos of 40. Can I rewrite cos of 40 as 60 minus 20? So let's start with this. So cos of 80 plus cos of 40. If I rewrite the 80, it would be 60 plus 20. If I rewrite the 40, it'll be 60 minus 20. So if you're going to use an angle which isn't special, because this is working towards cos 20, the other angle you use has to be special or an axis, because otherwise it's just going to compound your problem. Now that I can use my identity. So it's cos the first angle, cos the second angle, minus sine the first angle, sine the second angle. Next one, again an identity. So this is now plus cos the first angle times cos the second angle plus sine the first angle times sine the second angle. Now there might be some like terms, so let's check. Well, there's minus sine 60 sine 20, so yes, I could actually use special angles, but there's plus sine 60 sine 20, so they actually cancel each other out. So I land up just having those two, and I'm going to use special angles. So cos of 60 is a half. That's wonderful. So it's a half cos 20 plus a half cos 20. And a half plus a half is 1. So this lands up being with cos 20 degrees. So hopefully you're seeing the trend from question 1 all the way to question 5, example 1 to 5. They're all the same idea about either seeing an angle and rewriting it as a compound angle so that you can use the identity to help yourself. Don't forget that special angles are really useful here. Okay, our last example is example 6. And example 6 is what I call a Pythagoras type question, because it'll say without a calculator, and we would have done these in grade 10 and 11. So it says if sine alpha equals negative 3 over 5. So immediately they've told you something about alpha. They've told you sine is negative, which means your angle can't be there and it can't be there. Now they've told you that alpha is from 0 to 70, which is all the way there. So now I know it can't be there. So I know that alpha is somewhere there in quadrant 3. Now why do I need to know that? I need to know what the sine is of x and y. R is always positive. X will be negative in this context, and y will be negative in that quadrant. So I'm hoping you remember this type of example from grade 11. What they do is they give you one set of information, which helps you narrow your quadrant down to 2 quadrants. Then they give you a second set of information, which allows you to identify which quadrant you're working in. Why? So that you can go figure out the signs of x and y. Now I can use my identity here. Sine in the Cartesian plane is y over r. So r is 5, and the y must be the -3. Now how do we find x? We use Pythagoras. Now this is why you have to know what quadrant you're working in, because if you use Pythagoras, you just do a 3 squared plus what squared gives you 5 squared, and you get an answer as 4, and you never stop to think it could be -4. So don't forget to check the sign by using the quadrant. So this is why I call them Pythagoras type examples. Now that I know x, y, and r, you can do anything in terms of alpha. You can do sine of alpha, cos of alpha, tan of alpha. Now this question asks for cos of alpha plus beta. So now I need to go do exactly the same process, but with beta. So let's look at what I know about beta. First bit of information is cos is positive. So you're not there and it's not there. And now I tell you that sine is negative. Well, sine is positive in quadrant 1, so it can't be there. So beta is in quadrant 4. Now, why did I want to know this? Because then I can go and say, well, r is always positive. This y value would be negative. The x value would be positive. If I look at my definition, cos by definition is x over r. And then if I go and do Pythagoras, I'll get 12. Now, I'm not doing my Pythagoras here because these are what's called Pythagorean triples. So I know off by heart that 5, 12, and 13 is a Pythagorean triple. But if you don't know your Pythagorean triples, you could just do Pythagoras' theorem. Now, this should be a fairly easy question for me, because I know that cos of alpha plus beta, notice I haven't found alpha or beta because I'm not allowed to use a calculator. So I can't actually find their values, but I know the identity says it's cos alpha, cos beta minus sine alpha, sine beta. That's the identity. Now, because I have x, y, and r of everything, I can just go and use my definitions. So cos of alpha would be from here. Cos is x over r. Cos of beta, that would be from here. Cos is x over r. Okay, minus sine of alpha, that would be from here. Sine is y over r. And sine of beta would be from your beta Cartesian plane, which is y over r. And now I basically just need to simplify. So not too difficult. Here my 5's cancel, so I get minus 4 over 13. And a minus and a minus and a minus make a minus. And this starts to become a bit messy. And so we don't actually care if you use calculators here, because that's not what I'm trying to really get you to avoid using a calculator for. So I get 36 over 65, and I really would use a calculator now to combine those. So I wouldn't worry about by the time you get to this point, I would just use a calculator. So I get minus 56 over 65. I hope I did that right. So other than using a calculator for these annoying fractions, you don't use a calculator to actually find alpha and beta. So these are your stereotypical Pythagoras type questions from 10 and 11. It's just now that we've stepped it up because we've included a compound angle question. So really, really, really nifty. Right, and that's topic 2. So nothing drastically new, but just using these compound angle identities in exam type questions.